All right. Hello. Well, making sure all my sound's coming through. Let me know. Let me know if you can hear me good. All right. Hello. Well, let me know. Let me know if you can hear me good. All right.
Bluetooth disconnected.
I think that'll be better. All right. Now, just for some context to the title. I've been I don't know, things I've observed and noticed and started reading about and learning. Noticed there's some similarities in some crazy places. So, I've been doing some research and I wanted to share a little bit about, what interests me. This is the universe in the cell, and there's a lot of similarities. It kind of be surprising, and you have to work with me on pronunciation. I am probably not the greatest at pronouncing some of these words, some of these terms that are going to be in here. So work with me. Appreciate it. Sounds like I'm having recording my audio twice or something. See if we can fix that. Monitor off. Go ahead and give me a comment. Let me know what you think the audio gets better or not. Try to get this going. Get started here. Testing my audio again here so I can hear it. Yep, I still hear it. I got a little bit of a issue here with this. Figure that out here. Audio. That might be it. I might have just found it. Sorry, there's so many settings in so many different places for this. It's like if one setting's messed up. Alright, and now another test. Sorry. So, sounds like it's better. I think it's better. We'll try this. All right. Now these are just some key points and some things that I've been researching here about the universe and a cell and their similarities. All right. And let me get this screen up here. Is that the right one? Nope, it's not that one. This one. Jeez, this thing's always no. There it is. Here we go. There we go. I guys can see what I see here. See if I can get this to look a little better. Alright, I'm going to adjust this a little bit. I know, just thinking around here. Put it in somewhere in the center. Maybe, just maybe, it'll be legible. Alright. The universe in a cell. Cosmic and cellular connections. While they seem vastly different, the universe and a cell share some intriguing similarities. One, they both have a complex system with interconnected parts. The universe's galaxies, stars, planets, and other celestial bodies interact in intricate ways, forming a complex cosmic web. A cell. Organelles, like the nucleus, mitochondria, and endoplasmic reticulum, work together to maintain life, creating a miniature ecosystem. Remember, I'm working on pronunciations. 2. Energy and matter. The universe is composed of matter and energy governed by laws of physics and thermodynamics. Cell requires energy, ATP, and matter, nutrients, for growth, repair, and function. 3. Growth and expansion. Universe expanding at an accelerating rate. Cell grows and divides, increasing in size and number. Now, I think that's a little short, but there's a lot to the expanding at an accelerating rate versus universe to cell, because if you think of size difference to scale, you would have the time scale too, right? So the commonalities could be more closely, like maybe we expand and we turn into, multiple universes out of one later on, I don't know, hundreds of millions, if not hundreds of billions of years. I don't really know. Again, that's all, it's all just thoughts that come out of the brain. All right, and then 4, we have self-organization. The universe structures, like galaxies and solar systems, form through spontaneous self-organization. So, molecules assemble into organelles, which in turn form the cell, demonstrating self-organization. Patterns and structures. Universe exhibits patterns like a spiral galaxy and fractal structures. Cell contains intricate patterns in DNA, proteins, and cellular structures, all forming very similar structures. 6. Evolution and adaptation. The universe undergoes constant change and evolution with new stars and galaxies forming. Cells evolve through genetic mutation and natural selection. While these are broad comparisons, they highlight the underlying principles of complexity, organization, and dynamic change that govern both the cosmic and cellular realms. Each and matter, my apologies, energy and matter, the building blocks of existence, We touched on this briefly, but let's expand. Universe. The fundamental building blocks are matter, protons, neutrons, electrons, and energy, light, heat, etc. These combine to form everything from atoms to galaxies. Okay. A cell. Similarly, cells are constructed from matter, proteins, lipids, carbohydrates, nucleic acids, and require energy, ATP, to function. A key point. The laws of thermodynamics govern both systems. Energy is converted from one form to another, and matter is recycled and transformed. The role of matter in building complexity, from cosmic dust to cellular structures, matter. In it, various forms is the fundamental building blocks for complexity in both the universe and the cell. The universe. Gravitational attraction. Matter clumps together due to gravity, forming celestial bodies like stars, planets, and galaxies. Nucleosynthesis. Stars are cosmic forges where lighter elements transform into heavier ones, a process crucial for the creation of the matter necessary for life. Cosmic dust. The remnants of exploded stars provide the raw material for new stars, planets, and even life itself. The cell. Biomolecules. Matter is organized into complex molecules like proteins, nucleic acids, lipids, and carbohydrates, each with specific functions. Cellular structures. These molecules assemble into organelles, the cell's functional unit. Tissue and organ formation. Let me scroll down. Now we're back at tissue and organ formation. Cells group together to form tissues, which in turn form organs, demonstrating increasingly levels of complexity. An interesting parallel. Just as different elements combine in various proportions to create diverse celestial bodies, different combinations of biomolecules lead to the incredible variety of life on Earth. Self-organization and information, the architects of complexity. And then you get self-organizing order from chaos. Self-organizing is a fascinating phenomenon where complex patterns and structures emerge from simple interactions among components. It's a cornerstone of both cosmic and cellular systems. Galaxies, stars, and planets form through gravitational interactions, a classical example of self-organization. Even the intricate patterns found in nebulae showcase this principle. Cellular processes like protein folding, membrane formation, and cell division are driven by self-organization. It's the foundation for life's complexity. The blueprint of creation. Information is the currency of complexity. It guides the self-organization process, determining the form and function of systems. While we're still exploring the concept of cosmic information, some theories propose that fundamental laws of physics contain the information needed to create the universe. Like a cell, DNA has a genetic code, is the epitome of information in biology. It provides instructions for building and maintaining an organism. Information seems to be essential for directing self-organization. Without a blueprint provided by information, complex systems would likely be chaotic and unsecure. Like quantum mechanics, self-organization, and the origin of life. Quantum mechanics, the cosmic and cellular underpinnings. The physics of the very small play a role in both the vastness of the universe and the intricacies of a cell. Phenomenon like quantum fluctuations are thought to have been crucial in the early universe, potentially leading to the formation of the first structures. Quantum effects also influence processes within stars and black holes. Quantum tunneling is involved in essential biological process like photosynthesis and enzyme reaction. Quantum effects might even play a role in consciousness and DNA mutations. The interplay of self-organization, information, and quantum mechanics. These elements intertwine to create the complexity we observe. Quantum fluctuations as seeds. It's the commonality between seeds and, you know, the entire universe. Random quantum fluctuations could have acted as the initial seeds for self-organization in the early universe, leading to the formation of matter and energy structures. Quantum tunneling in biology. This quantum phenomenon allows for efficient energy transfer and complex molecular interactions, essential for self-organization within the cell. Information and quantum information. DNA, the carrier of biological information, might be influenced by quantum effects. It's like, all sorts of invisible forces. You get vibrations, sound. It's all, you could feel it. It can have an effect on anything. You know, like just one vibration in this area might have changed that tree to, face, turn a little bit or just be in a different spot than where it was. I mean, it's simple. Um, yeah, I got that. Okay. We are quantum driven self organization. Perhaps life emerged from a self organizing system influenced by quantum effects where information gradually emerged to guide the process. The quantum biology. Understanding the role of quantum mechanics in biological processes could revolutionize our understanding of life's origins and evolution. Challenges in exploring the quantum universe and cell connection. The intersection of quantum mechanics, biology, and cosmology is a fascinating but challenging frontier. Here are some of the primary hurdles. At the bottom, and in the bottom, I have all my sources. They're all web links to where I was doing research. Let's see. One would be bridging the quantum classical divide. Complexity. Biological systems are incredibly complex, operating primarily at the classical scale. Isolating and studying quantum effects within this environment is extremely difficult. Decoherence. Quantum states are fragile and easily disrupted by interactions with the environment. Like just by looking at them, it can change the effect. Like we did this experiment with quarters where you can basically like link the quarters together and then I could guess your quarter and it worked literally 99.9% of the time. I mean, we ran it 20 times and got 20 out of 20. We ran it 30 times and got like 29 out of 30. We ran it 40 times and got 40 times. So it's literally like 99.9% when you can intertwine the coins, then they can be viewed in separate locations and you can get the effect. You can see how they're intertwined where one will land heads, the other will land tails every single time. It's crazy. I've done it. All right. Let's see. We were decoherent quantum states. We just finished that. Experimental limitations. Sensitivity. Detecting and measuring quantum phenomena in biological systems requires incredibly sensitive instruments and techniques, which are still under development. Right. We don't. This is again technology. that's needed that we're not to yet, but we're working on. We know where it is. We know how to get to it. We're researching and building. Okay. Theoretical framework. Move this up a little bit, getting down there. Oh, way cool. Theoretical framework. Integration developing unified theoretical framework that can seamlessly connect quantum mechanics, biology, and cosmology is a complex task. There are multiple interpretations of quantum mechanics, which can lead to different approaches and challenges in applying it to biological systems. Basically, like, as one word can mean many words, the interpretation is very important, and you really got to be careful. You got to basically repeat it a million times, repeat it a million times, interpret every way as possible, and see which way is seems to be viable. Anyway, all right, reproductivity, biological variability. Biological systems are inherently variable, making it difficult to reproduce experimental results and draw definitive conclusions. Yeah, that's where the one little vibration could change the whole thing. One little, uh, drop of something else, one mixing it, basically, there's too many variables. It's like there's a lot going on, and to do the same thing repetitively, exactly the same way, the exact same amount of time, the exact same time it hit the air, same time. Again, it's really hard to do. So it's very problematic to get, a guaranteed answer. Then you have quantum uncertainty. The probabilistic nature of quantum mechanics adds another layer of complexity to reproducibility. All right, moving on. Interdisciplinary collaboration. Language barriers. Oh, yeah, that's a big one that we get a lot. When you live in a very diverse community, man, it can get challenging to communicate, but, for many reasons. But hand signals are somewhat universal, man. All right. Effective communication between physicists, biologists, and cosmologists is essential, but often hindered by different terminologies and perspectives. Resource allocation. Securing funding and support for interdisciplinary research can be challenging. Yeah, getting the money to do all this stuff is always been a problem. That's why we're trying to build society the way we are, so we can group large amounts of money together to purchase larger things. It's like getting a mortgage to buy your house, right? You get a bunch of companies that invest into this one bank, so this bank can use their money to loan you money, so that you pay it back with interest, so they gain money, and then everybody gets their percentage of profit off of it. So, same concept there. All right. Allocating the funding, addressing these challenges will require significant investments in both theoretical and experimental approaches. Despite the difficulties, the potential rewards of understanding the quantum foundations of life and the universe are immense. Potential solutions and research directions. Overcoming the challenges in exploring the quantum universe and cell connections will require a multidisciplinary approach and significant investment in research. Here are some potential solutions and research directions. All right, where are we at? Right. Good enough for the moment. All right. 1. Technological advancements. Quantum sensors. Developing highly sensitive quantum sensors to detect and measure quantum effects in biological systems. Quantum computer. Leveraging quantum computers to simulate complex biological processes and model quantum interactions. Cryogenic biology. Studying biological systems at extremely low temperatures to reduce decoherence and observe quantum effects. Slow things down so maybe they're not happening so fast so that you can actually get a good look at it, right? Interdisciplinary collaboration. Centers of excellence, establishing dedicated research centers that bring together physicists, biologists, and cosmologists to foster collaboration. Training programs, developing interdisciplinary training programs to equip scientists with the necessary skills to bridge different fields. Theoretical framework development. Quantum biology theories, creating robust theoretical frameworks to explain quantum phenomena in biological systems. To me, in a lot of ways, theoretics is really just kind of like sit back and look and just kind of use your imagination on why something would happen, right? And just pull it out of the air, pull it out of the air. Be like, okay, well, I think this is because of this, and then finding a process in which to test that with, and build something that kind of says, okay, this could work. This theoretically could work, and then keep doing that process, right? Until you get to where you can repeat the process over and over again, and then you get the same result over and over again. All right, quantum cosmology connections, exploring potential connections between quantum mechanics and cosmological models. Just similarities, right? Because you're thinking that you're looking at a microscope that we can't even. It's so small versus a universe, a system that is huge. Like, I mean, beyond comprehension, huge. So you have to basically be able to take yourself out of your own universe, sit back, and make your universe shrink down to the size of a cell. There's a lot of things that are very similar there. All right, darn it, where was I? I kind of got lost on that one. I'm gonna take a drink. Thirsty. Okay, now I gotta look. I think I did theoretical framework last, I believe. So it would be at model, organisms, and systems. All right, so simplified systems. Studying simpler organisms or isolated biological systems to reduce complexity and focus on specific quantum effects. Synthetic biology, designing and building artificial biological systems to test specific quantum hypotheses. Data science and machine learning. Data analysis, utilizing advanced data analysis techniques to extract meaningful information from complex biological data. Predictive modeling, developing models to predict quantum behavior in biological systems. Again, a lot of these are going to be very similar because, things you have to do. It's the process, right? 6. Ethical considerations. Quantum ethics, addressing the ethical implications of quantum technologies, particularly in biology and medicine. Public engagement, promoting public understanding of quantum science and its potential impact on society. Like the cure-all, like if we could understand quantum on the biological level, then we could cure everybody and nobody would ever have to die and we could all live forever. That could be a good thing and it could be a bad thing. So, All right, moving on. Let's see. Now we're on ethical considerations. Right. Because, this world's screwed up. So, ethics. That's a tough one. Quantum ethics, addressing the ethical implications of quantum technologies, particularly in biology and medicine. Public engagement. Oh, wait a minute. Huh. Promoting public understanding. That's what I just. Yep. Sorry, I went back on there. I see now. I thought that sounded familiar. It's like I've read that thing too many times. That's why. By combining these approaches, researchers can gradually unravel the mysteries of the quantum universe and its connections to life. My little bit of artwork that I did. Well, okay. I obviously didn't make that, but I gave the idea to have that made. So all the art on here is just concepts. If you made the universe look like a cell, or if a cell in the universe, you know. Anyway, incompletion. Implications of exploring the quantum universe and cell connection. Understanding the intricate relationship between the quantum world and biological systems has profound implications across various fields. Medicine and healthcare. Quantum medicine. Development of novel diagnostic tools and therapeutic approaches based on quantum principle. Drug discovery. Accelerated drug discovery process by simulating molecular interactions at a quantum level, like being able to build a quantum computer that could basically, its focus was to make you know, take this molecule and build all these different medicines on how they react to like the human body for humans, we'll say, and how they're, they can simulate out the reactions with all the different chemicals inside of your body with whatever chemicals in this to see if you can get the right mixture to, fix the problem. So it just makes things quicker. Interactions at the quantum level. Personalized medicine. Tailored treatments based on individual genetic and quantum biological profiles. Technology. Quantum computing. One of the things I just said. Breakthrough in computing power with applications in fields like cryptography, materials science, and drug design. Quantum sensors. Development of highly sensitive sensors for various applications, including environmental monitoring and medical imaging. Right, they'll be able to scan your body with a scanner and know where everything is, every vein, every muscle, every piece of tissue, and never have to actually go in. And maybe we can stop radiating ourselves for X-rays. That'd be great, wouldn't it? Quantum communications, secure and efficient communication networks, super fast, super reliable, even in a storm. Fundamental science, origin of life, new insights into the emergence of life and the role of quantum process and biological evolution. Consciousness, exploration of the potential quantum basis of consciousness. Universe formation, deeper understanding of the early universe and the role of quantum fluctuations in cosmic structure formation. Philosophical and ethical implications. What? Redefining reality. Challenges to our classical understanding of the world and the nature of reality. Ethical considerations. Addressing ethical implications of quantum technologies such as privacy, security, and potential misuse. Yeah, because we live in that kind of world where everybody just wants to misuse everything. People be digging with a freaking butter knife instead of a freaking shovel, I swear. Okay, addressing ethical implications of quantum technologies such as privacy, security, and potential misuse. It's important to note that many of these implications are speculative and based on potential breakthroughs. However, the potential impact of understanding the quantum foundations of life and the universe is immense and could revolutionize multiple fields, like everything, right? Anything and everything. And when you think about quantum, it's like being able to store information in a total other dimension, and then go into that dimension and pull that information out. I would say with space, right? Because then you could store things in the same exact space and time. Wouldn't that be interesting? All right, moving on. All right. Cells and the universe have some similarities, including cell cytoplasm and neutron stars. Both have structures that resemble multi-story parking garages. Cell membranes. Cells have specialized proteins in their membranes that transport molecules across the membrane. Some of these proteins have been preserved over time and can be found in distantly related organisms. Cell reproduction. Cells reproduce by splitting in two, creating daughter cells that can then divide and grow. Get all sorts of notifications. Wow. All right, cells reproduce by splitting in two. Yep, covered that. Cell energy. Cells are adenosine. I'm gonna pronounce this wrong. This is where I get to where I had to, a lot of the stuff I had to look up how to spell properly while I was, again. This probably took me 10 times longer than it would take a normal person, right? Okay, so anyway, cells use adenosine 5 triphosphate ATP. Right. That's what I was remembering it as was ATP. ATP is so much easier. To create energy for activities like movement and synthesizing cell components. The mechanisms used to generate ATP may have evolved in 3 stages, which could have changed Earth's atmosphere and cell and universe size. Interesting. All right. And then below this, like down here is all my sourcing from all the locations where I got all my information from. All right. Well, here, you know what? I'll just leave it down there so you can always want to type that out. The number of cells in a living being, atoms in a cell, galaxies in the universe, the stars and the galaxy are all roughly the same large number, 10 to the 11th and 10 to the 14th. Very similar, very close, and could the difference just be that we are this and that is that? Possibly. Cells in the universe complexity. Some say that physicists view humans as a complex system made up of many simple atoms, similar to how cells can be thought of as their own universe. Some say that a cell can be a universe. For example, Grant R. Jeffries' book Creation suggests that each human cell is a universe in itself. I've always believed a lot of this kind of stuff, like in is out, right? You got infinite, and you can get smaller infinitely as you can get bigger infinitely, and it's like every time you just slip into the new, you're getting bigger, 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 you're getting smaller, smaller, smaller. Maybe you're doing both. Maybe you're going up one side and down the other, and it's like a loop where you keep going back all the way around. Who knows, right? All right. See, and I can get carried away. Okay, where I was talking about the creation suggests that each human cell is a universe in itself, and that smaller universe cells combine to form larger universe organs. These organs then come together to form the physical body, and all human bodies together make up the Earth. Huh. Well, I mean, that one's a little bit out there as far as the human bodies together to make up the Earth, because these, I mean, I guess if we get biblical, it says we were made out of clay, so I guess that might even make sense there. Who knows? But it's just the similarities, and they're real close. Hmm. The book also suggests that humans are a summary of how the physical universe outside of our own universe are made. A holographic strategy called the cellular universe also suggests that nearly everything in the macroverse is mirrored in the biological cell as a microverse. This strategy could be useful for designing hypotheses for cosmological research projects and could also provide insights into the inner workings of the cosmos. Well, that is it. Let me know what you think. Like I said, it's just something that caught my thoughts, and I decided, well, I'm going to do some research. I'll put some stuff together, and I'm going to read it. And it's just because I've always felt like, throughout the universe, that inside of us is the same thing that's outside of us, and it's infinitely in as it is infinitely out. And there's no real beginning and there's no real end, that there's always was, right? So, but from different perspectives, you know. But definitely leave me some comments. Let me know what you think. I'm gonna do this more often and hopefully get better at it, you know. So all I can do is get better. Thanks for checking it out. Like, subscribe, share, or don't.